When dealing with electrical installations, understanding conductor derating and load diversity is crucial for ensuring safety and compliance with the National Electrical Code, or NEC. The scenario involves 22 number 12 conductors and a number 12 ground wire in a 1 and 1/4-inch electrical metallic tubing, or EMT, conduit, feeding computer workstations. The key consideration is where the derating is required, given that the workstations won't be fully active all the time, and even when active, not all circuits will be in use. Let's delve into how to approach this situation using the NEC. Table 310.15 B2 addresses the issue of conductor derating when multiple current-carrying conductors are bundled together in a raceway or cable. This table provides adjustment factors to reduce the allowable ampacity of conductors based on the number of current-carrying conductors. These adjustment factors are designed to prevent overheating of the conductors, which can lead to insulation damage and potentially create a fire hazard. However, the applicability of Table 310.15 B2 hinges on whether the conductors are fully loaded or operating at their rated ampacity. If the conductors are not fully loaded, the full derating factor may not be necessary. In the context of computer workstations, it's unlikely that all circuits will be operating at their maximum capacity simultaneously. This is where the concept of load diversity comes into play. Load diversity refers to the fact that in many electrical systems, the total connected load is not equal to the actual load being drawn at any given time. This is because not all devices or equipment operate at their maximum capacity simultaneously. Annex B of the NEC provides tables and guidelines for applying load diversity factors. Specifically, Table B 310.11 provides load diversity factors for various types of electrical loads. The load diversity factor represents the percentage of the total load that is expected to be simultaneously utilized. For computer workstations, which are known for their intermittent usage and varying power demands, a load diversity factor can be applied. The NEC allows for the application of these factors to more accurately reflect the actual load on the conductors. To determine the appropriate load diversity factor, refer to Annex B, Table B 310.11. This table provides diversity factors for different types of loads, including office buildings and computer workstations. According to the table, the load diversity factor for computer workstations is typically around 70%. This means that only 70% of the total connected load is expected to be utilized simultaneously. This factor accounts for the fact that not all workstations will be operating at full capacity at the same time, and some workstations may be idle or in low power mode. Now, let's apply this load diversity factor to the scenario with the 22 number 12 conductors in a 1 and 1/4-inch EMT. The first step is to determine the maximum allowable ampacity for number 12 THHN copper conductors in the EMT. According to Table 310.16 of the NEC, the maximum allowable ampacity for number 12 THHN copper conductors is 25 amps. This is based on the assumption that the conductors are operating at an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit, and that there are no more than 3 current-carrying conductors in the raceway or cable. However, since we have 22 number 12 conductors in the EMT, we need to consider the derating factors outlined in Table 310.15. B2. This table provides adjustment factors based on the number of current-carrying conductors. For 22 conductors, the adjustment factor is 50%. This means that the allowable ampacity of the conductors must be reduced by 50%. However, before applying this derating factor, we can first apply the load diversity factor. Since the load diversity factor for computer workstations is 70%, we can adjust the allowable ampacity by multiplying it by 0.70. Adjusted ampacity equals 25 amps multiplied by 0.70, which equals 17.5 amps. This means that the adjusted ampacity for the number 12 conductors, taking into account the load diversity factor, is 17.5 amps. Now, we need to compare this adjusted ampacity to the actual load in the conductors. The NEC requires that the conductors be sized to carry the non-continuous load plus 125% of the continuous load. In this case, since the computer workstations are not expected to be operating at full load continuously, we can assume that the load is non-continuous. This means that we only need to size the conductors to carry the actual load. To determine the actual load, we need to know the current draw of each computer workstation. Let's assume that each workstation draws a maximum of 1.5 amps. This is a reasonable assumption for typical computer workstations. Since we have 22 workstations, the total load is 22 workstations multiplied by 1.5 amps per workstation, which equals 33 amps. However, since we have applied a load diversity factor of 70%, the actual load is 33 amps multiplied by 0.70, which equals 23.1 amps. Now, we can compare this actual load to the adjusted ampacity of the number 12 conductors. The adjusted ampacity is 17.5 amps, while the actual load is 23.1 amps. This means that the number 12 conductors are not large enough to carry the actual load. Therefore, we need to either increase the size of the conductors or reduce the load. One option is to increase the size of the conductors to number 10 THHN copper conductors. According to table 310.16, the maximum allowable ampacity for number 10 THHN copper conductors is 30 amps. Applying the same load diversity factor of 70%, the adjusted ampacity becomes 30 amps multiplied by 0.70, which equals 21 amps. This is still not enough to carry the actual load of 23.1 amps. Another option is to reduce the load by reducing the number of workstations or by using more energy-efficient workstations. If we reduce the number of workstations to 18, the total load becomes 18 workstations multiplied by 1.5 amps per workstation, which equals 27 amps. Applying the same load diversity factor of 70%, the actual load becomes 27 amps multiplied by 0.70, which equals 18.9 amps. This is now less than the adjusted ampacity of the number 12 conductors, which is 17.5 amps. Therefore, we can use number 12 THHN copper conductors to feed 18 computer workstations. In summary, when dealing with conductor derating and load diversity, it's important to consider the following factors. Firstly, determine the maximum allowable ampacity for the conductors based on their size, insulation type, and installation method, referring to NEC table 310.16. Secondly, assess whether the conductors are fully loaded or operating at their rated ampacity. If the conductors are not fully loaded, consider applying a load diversity factor using NEC Annex B, table B, 310.11 to more accurately reflect the actual load in the conductors. Thirdly, calculate the adjusted ampacity by multiplying the maximum allowable ampacity by the load diversity factor. Fourthly, determine the actual load on the conductors taking into account the non-continuous and continuous loads. Fifthly, compare the adjusted ampacity to the actual load to ensure that the conductors are adequately sized. If the actual load exceeds the adjusted ampacity, increase the size of the conductors or reduce the load. By carefully considering these factors and following the guidelines in the NEC, you can ensure that your electrical installations are safe, compliant, and efficient. In this specific scenario, it was determined that number 12 THHN copper conductors in a 1 and 1/4 inch GMT were not adequate to carry the load of 22 computer workstations, even after applying a load diversity factor. Therefore, it was necessary to either increase the size of the conductors or reduce the number of workstations. It's always recommended to consult with a qualified electrical engineer or inspector to ensure that your electrical installations comply with all applicable codes and standards. Now let's revisit derating factors for more than 3 current carrying conductors in a raceway or cable, as outlined in NEC table 310.15. V2. This table provides adjustment factors that reduce the allowable ampacity of conductors based on the number of current carrying conductors in a raceway or cable. These adjustment factors are designed to prevent overheating of the conductors, which can lead to insulation damage and potentially create a fire hazard. The adjustment factors in table 310.15. B2 are based on the assumption that all the conductors are carrying current simultaneously. However, in many electrical systems, this is not the case. As discussed earlier, load diversity refers to the fact that in many electrical systems, the total connected load is not equal to the actual load being drawn at any given time. This is because not all devices or equipment operate at their maximum capacity simultaneously. When applying Derating factors, it's important to consider whether the conductors are fully loaded or whether load diversity can be applied. If the conductors are not fully loaded, the full Derating factor may not be necessary. In some cases, it may be possible to apply a reduced Derating factor or to eliminate the Derating factor altogether. To determine whether load diversity can be applied, it's necessary to analyze the load characteristics of the electrical system. This involves identifying the types of loads, the duty cycles, and the relief het til ugravalif lamiet tekmabital of operating simultaneously. Based on this analysis, a load diversity factor can be determined. This factor represents the percentage of the total connected load that is expected to be utilized simultaneously. Once the load diversity factor has been determined, it can be used to adjust the Derating factors in Table 310.15. B2. To do this, multiply the Derating factor by the load diversity factor. The result is the adjusted Derating factor. This adjusted Derating factor can then be used to calculate the allowable ampacity of the conductors. In the example with the 22 number 12 conductors in a 1 and 1/4 inch EMT, the Derating factor from Table 310.15 B2 is 50%. However, since we have applied a load diversity factor of 70%, the adjusted Derating factor becomes 50% multiplied by 70%, which equals 35%. This means that the allowable ampacity of the conductors must be reduced by 35%. To calculate the allowable ampacity, multiply the maximum allowable ampacity of the conductors by 1 minus the adjusted Derating factor. In this case, the maximum allowable ampacity of number 12 THHN copper conductors is 25 amps. Therefore, the allowable ampacity is 25 amps multiplied by 1 minus 0.35, which equals 16.25 amps. This means that the number 12 conductors can carry a maximum of 16.25 amps without exceeding their temperature rating. It's important to note that the application of load diversity factors and adjusted Derating factors requires careful engineering judgment and a thorough understanding of the electrical system. It's always recommended to consult with a qualified electrical engineer or inspector to ensure that your electrical installations comply with all applicable codes and standards. Now, let's address the situation with the number 12 ground wire and the 1 and 1/4 inch EMT. The NEC requires that all electrical systems be grounded to provide a safe path for fault current to return to the source. The size of the ground wire is determined by the size of the ungrounded conductors. In this case, the ungrounded conductors are number 12 THHN copper conductors. According to Table 250.122 of the NEC, the minimum size of the ground wire for number 12 ungrounded conductors is number 12 copper. Therefore, the number 12 ground wire in the 1 and 1/4 inch EMT is adequately sized. However, it's important to ensure that the ground wire is properly connected to the equipment grounding system. This involves connecting the ground wire to the metal enclosure of the equipment, such as the computer workstations, and to the grounding electrode system, such as the ground rod or metal water pipe. Proper grounding is essential for electrical safety. It helps to prevent electric shock and equipment damage in the event of a fault. It also helps to reduce electromagnetic interference, which can disrupt the operation of electronic equipment. In addition to the size and connection of the ground wire, it's also important to consider the impedance of the grounding path. The NEC requires that the impedance of the grounding path be low enough to allow sufficient fault current to flow to trip the overcurrent protection device, such as a circuit breaker or fuse. This ensures that the fault is quickly cleared, minimizing the risk of electric shock and equipment damage. To minimize the impedance of the grounding path, it's important to use short, direct grounding conductors and to avoid sharp bends or loops. It's also important to ensure that all connections are tight and free of corrosion. In summary, the number 12 ground wire in the 1 and 1/4-inch EMT is adequately sized for the number 12 and grounded conductors. However, it's important to ensure that the ground wire is properly connected to the equipment grounding system and that the impedance of the grounding path is low enough to allow sufficient fault current to flow. Proper grounding is essential for electrical safety and equipment protection. Now, let's consider the impact of ambient temperature on conductor ampacity. The NEC specifies that conductor ampacities are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. However, in many electrical installations, the ambient temperature may be higher than this. When the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductors must be reduced to prevent overheating. The NEC provides correction factors in Table 310.15 B2 that are used to adjust the ampacity of conductors based on the ambient temperature. These correction factors are based on the insulation type of the conductors. Different insulation types have different temperature ratings. For example, THHN insulation has a temperature rating of 90 degrees Celsius or 194 degrees Fahrenheit, while TW insulation has a temperature rating of 60 degrees Celsius or 140 degrees Fahrenheit. To determine the appropriate correction factor, refer to Table 310.15 B2 and find the correction factor for the insulation type and the ambient temperature. Multiply the maximum allowable ampacity of the conductors by the correction factor. The result is the adjusted ampacity. For example, if the ambient temperature is 40 degrees Celsius or 104 degrees Fahrenheit and the conductors have THHN insulation, the correction factor is 0.91. This means that the allowable ampacity of the conductors must be reduced by 9%. To calculate the allowable ampacity, multiply the maximum allowable ampacity of the conductors by 0.91. In the example with the 22 number 12 THHN copper conductors in a 1 and 1/4-inch EMT, the maximum allowable ampacity is 25 amps. Therefore, the allowable ampacity at 40 degrees Celsius is 25 amps multiplied by 0.91, which equals 22.75 amps. It's important to note that the ambient temperature is the temperature of the air surrounding the conductors. This may be different from the room temperature. For example, if the conductors are installed in a confined space with poor ventilation, the ambient temperature may be significantly higher than the room temperature. In such cases, it's important to measure the ambient temperature as close as possible to the conductors. In addition to ambient temperature, other factors can also affect conductor ampacity. These include the proximity of other heat-generating equipment, the altitude of the installation, and the presence of direct sunlight. The NEC provides guidelines for addressing these factors. In summary, ambient temperature can have a significant impact on conductor ampacity. It's important to consider the ambient temperature when sizing conductors and to apply the appropriate correction factors. Proper consideration of ambient temperature is essential for preventing overheating and ensuring the safe and reliable operation of electrical systems. Now let's discuss the use of 90 degrees Celsius rated conductors. The NEC allows the use of conductors with a 90 degrees Celsius insulation rating, such as THHN or XHHW, for certain applications. However, it's important to understand the limitations and requirements for using these conductors. The primary advantage of using 90 degrees Celsius rated conductors is that they have a higher ampacity than conductors with lower temperature ratings, such as 75 degrees Celsius or 60 degrees Celsius conductors. This means that smaller conductors can be used to carry the same amount of current, which can save space and reduce costs. However, the NEC imposes certain restrictions on the use of 90 degrees Celsius rated conductors. One restriction is that the ampacity of the conductors must be based on the 75 degrees Celsius column in Table 310.16 unless certain conditions are met. These conditions include the following. Firstly, the conductors must be installed in a raceway or cable. Secondly, the terminations of the conductors must be rated for 90 degrees Celsius. Thirdly, the equipment connected to the conductors must be rated for 90 degrees Celsius. If these conditions are met, the ampacity of the conductors can be based on the 90 degrees Celsius column in Table 310.16. However, even if these conditions are met, it's important to consider the temperature limitations of the equipment connected to the conductors. If the equipment is not rated for 90 degrees Celsius, the ampacity of the conductors must be reduced to match the temperature rating of the equipment. For example, if the equipment is rated for 75 degrees Celsius, the ampacity of the conductors must be based on the 75 degrees Celsius column in Table 310.16. In the example with the 22 number 12 THHN copper conductors in a 1M1/4-inch EMT, the conductors have a 90 degrees Celsius insulation rating. However, unless the terminations and equipment are also rated for 90 degrees Celsius, the ampacity of the conductors must be based on the 75 degrees Celsius column in Table 310.16. This means that the maximum allowable ampacity of the conductors is 20 amps, rather than 25 amps. It's also important to consider the temperature limitations of the overcurrent protection device, such as a circuit breaker or fuse. The overcurrent protection device must be rated for the same temperature as the conductors. If the overcurrent protection device is not rated for the same temperature as the conductors, the ampacity of the conductors must be reduced to match the temperature rating of the overcurrent protection device. In summary, 90 degrees Celsius rated conductors can be used to increase ampacity, but certain conditions must be met. The ampacity of the conductors must be based on the 75 degrees Celsius column in Table 310.16, unless the terminations and equipment are rated for 90 degrees Celsius. It's also important to consider the temperature limitations of the equipment and overcurrent protection device. Proper consideration of temperature limitations is essential for preventing overheating and ensuring the safe and reliable operation of electrical systems. Now let's talk about conduit fill. The NEC specifies the maximum percentage of the cross-sectional area of a conduit that can be occupied by conductors. This is known as conduit fill. The purpose of conduit fill is to prevent overheating of the conductors and to allow for easy installation and removal of the conductors. The NEC provides tables in Chapter 9 that specify the maximum allowable conduit fill for different types of conduits and conductors. These tables are based on the type of conduit, the size of the conduit, and the number and size of the conductors. To determine the conduit fill, first calculate the cross-sectional area of each conductor. The NEC provides tables in Chapter 9 that list the cross-sectional area of different sizes and types of conductors. Add up the cross-sectional areas of all the conductors and the conduit. Divide the total cross-sectional area of the conductors by the cross-sectional area of the conduit. The result is the conduit fill. The conduit fill must not exceed the maximum allowable conduit fill specified in the NEC tables. In the example with the 22 number 12 THHN copper conductors and 1 number 12 ground wire in a 1M1/4-inch EMT, the total number of conductors is 23. According to Table C1 in Annex C of the NEC, a 1M1/4-inch EMT can accommodate 23 number 12 THHN conductors. Therefore, the conduit fill is within the allowable limits. However, it's important to note that this is based on the assumption that all the conductors are the same size and type. If there are conductors of different sizes or types, the conduit fill may be different. It's also important to consider the bending radius of the conduit. The NEC specifies minimum bending radii for different sizes and types of conduits. The bending radius must be large enough to prevent damage to the conductors. In addition to conduit fill, other factors can also affect the ease of installation and removal of conductors. These include the length of the conduit run, the number of bends in the conduit, and the presence of obstructions. It's important to consider these factors when designing an electrical installation. In summary, conduit fill is an important consideration when designing electrical installations. The NEC specifies the maximum allowable conduit fill to prevent overheating of the conductors and to allow for easy installation and removal of the conductors. It's important to consult the NEC tables to determine the maximum allowable conduit fill for different types of conduits and conductors. Finally, let's consider voltage drop. Voltage drop is a decrease in voltage that occurs along a conductor due to the impedance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. To calculate voltage drop, use Ohm's law. Voltage drop equals current multiplied by impedance. The current is the current flowing through the conductor. The impedance is the resistance of the conductor plus the reactance of the conductor. The resistance of the conductor depends on the size, material, and length of the conductor. The reactance of the conductor depends on the frequency of the current and the spacing between the conductors. The NEC provides tables in Chapter 9 that list the resistance and reactance of different sizes and types of conductors. To reduce voltage drop, use larger conductors, shorter conductor lengths, or conductors with lower impedance. You can also use transformers to step up the voltage at the source and step it down at the load. In the example with the 22 number 12 THHN copper conductors in a 1 and 1/4 inch ENT, the voltage drop will depend on the length of the conduit run and the current flowing through the conductors. If the conduit run is long or the current is high, the voltage drop may exceed the NEC recommendations. In such cases, it may be necessary to use larger conductors or to reduce the load. Voltage drop is an important consideration when designing electrical installations. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. It's important to calculate voltage drop and to take steps to minimize it. In summary, understanding and applying the principles of conductor derating, load diversity, ambient temperature correction, conduit fill, and voltage drop are essential for designing safe, efficient, and code-compliant electrical systems. Always refer to the latest edition of the National Electrical Code and consult with qualified professionals for specific applications and interpretations.